All right. Good evening, everyone. So this is I welcome you all to the week 5 problem solving session of the course Aero Engine Gas Turbine Cycles. Um, so I think currently no one has joined, so probably most of you I think may be busy and would be viewing this recording in YouTube. Um, so as usual, I'm going to solve one problem today. Um, uh, Related to turbofan engines. And if you have any doubts regarding this problem, you can always come back next week and ask me. Okay. So without much delay, I'm going to just go through what we studied in this week's lecture. So this week's we introduced turbofan engines, and uh, we studied turbojet engines for last 2 weeks, and we found out that turbojet engine has a higher thrust to weight ratio. It has high exhaust velocity. It has high specific thrust. It requires short takeoff distance, and it also have a better specific range. But what we also need is we wanted to have a lower thrust to weight ratio, uh, which means we need to get as much as thrust with a very less weight. And uh, one way to do that is to, you know, uh, either increase the mass flow rate or increase the exit velocity. Increasing exit velocity requires we to add the afterburner, and that reduces the uh, that increases the fuel consumption and reduces the efficiency. We saw that in last week. We also solved a problem and we showed that efficiency drops and uh, the specific fuel consumption increases. So in but there is also another way that you can increase is through mass flow rate. But mass flow rate will make the engine bigger and bigger. So instead, what people try to do is they try to make the core engine as smaller and had a bypass flow to the engine. So that's how turbofan came into picture. So we have a big fan in front of the core engine, which has like compressor, turbine, and compressor, combustion chamber, and turbine like nozzle. Before all these components, we have a big fan, which actually compresses air to a certain amount and divides the flow into two different streams. One is bypass stream, another is a core stream. Core stream enters the core engine, undergoes compress and goes through compressor, combustion chamber, turbine, and nozzle. The other stream, bypass stream, will just go through a fan nozzle and exits with a higher velocity. So in this way, you are simplifying the component. You just have a fan which is going to compress the air and expand it, and uh, there you will not get a very high velocity in the bypass stream. However, since mass flow rate now becomes larger, you are going to get a higher thrust. And this is also a most effective way because the overall exit velocity reduces and hence propulsive efficiency increases. So that is the idea behind turbofan engines. You have a bypass flow, so typically people divide it into two different ways. One is low bypass ratio engine, another is a high bypass ratio engine. In low bypass ratio engines is typically used for stealth purposes, to mask the uh, you know IR signatures from the exit of the nozzle, from the core engine, and typically, as usual, they are used for military aircrafts. And for high bypass ratio engines, they are used in the commercial aircrafts because they have a very high propulsive efficiency and the specific fuel consumption is much lower compared to the turbojet engines, and that's why people prefer, I mean, it has been preferred that turbofan engine is to be used. So the bypass ratio is defined as m dot fan by m dot core, and uh, so the advantage is like fan is so there's also a propeller engine where you have a very big propeller, and it has the adding a propeller would also provides higher thrust, but it also comes with a lot of vibrations. However, fan is not as big as propeller, so it is confined, and the flow is confined, and hence you have a very stable engine with stable propeller, which has reduced vibrations. Aerodynamics is better controlled. It has a smaller gearbox and few more another efficiencies. As I said, fuel efficient design. So, and there is also like an optimized, I would not call optimized, but as you increase the bypass ratio, how the propulsive efficiency increases, you can see. By adding, bypass ratio, it increases, uh, it varies, it increases very quickly in the beginning, but after a certain bypass ratio, it gives a diminishing returns, which means it does not vary much. So typically the current bypass ratio that typically is being used is 12:1, and currently newer engines are coming up with ultra high bypass ratio engines, where they go till 16 to 1, which means 16 times the mass flow rate of the core engine is what flows in the bypass. Okay, so which means the engine is going to be very big and core is going to be very small. And the turbofan engines are typically divided as a forward fan and aft fan engines. In forward fan, we are currently studying forward fan engines. Forward fan, you have mixed and unmixed, where mixed means you have bypass stream and the core stream mixes at later stages. In unmixed, bypass stream exits the nozzle separately and core stream exits the nozzle separately. In the mixed, you also have a non-afterburner and afterburner cases. And similarly, in you can also divide the turbofan engines as high bypass ratio and low bypass ratio turbofan engines. Um, Low bypass ratio turbofan engines can have afterburner and no afterburner. The forward fan engines can also be further classified as single spool, dual spool, and three spool engines, where these can be geared or ungeared. So the reason to have a gearbox, we will study that in detail in the upcoming weeks. Okay. Um, the first configuration that we studied is a forward fan unmixed single spool configuration, where you do not have a mixing of core stream and the bypass stream. The bypass stream will get compressed as it flows through the fan, and it gets expanded in the fan nozzle, and the core stream goes through all the components in the core engine, and then it expands in a separate core nozzle. Okay, and the TS curve. So there is not much of a differences in the way of calculation. We just need to, instead of calculating the terminal temperatures and pressures of compressor right after the inlet, we also have a fan is nothing but an additional compressor which has its own pressure ratio. So whatever the compressor formulas that we use we are going to use the same for the fan, and we are just adding another component in front of the compressor. Okay, so that's the main thing. So we have a forward fan, we have a fan pressure ratio as pi f, and it also has an isentropic efficiency. So based on that, you can construct these formulas. And after the fan, you have the compressor for the core engine. After the fan, you have the fan nozzle for the bypass uh, you know stream. So you have compressor, combustion chamber, turbine, which is going to go through same logic, but only additional thing is now the turbine has to drive both compressor and fan. So what you have is the energy balance will differ a little bit. The work done or uh, you know work done by the air on the turbine is actually used to compress the air in the compressor, and also it is used to compress the air in the fan. Okay, so we need to add two work dones here while calculating the terminal temperatures of turbine. And then you have two nozzles, so that's the main updates. One is fan, another is turbine. You have to add an additional work done term, and finally you need to additionally calculate for how the flow stream exits from the fan nozzle. So in the fan nozzle, again, you have to find out critical pressure ratio. If the pressure ratio is higher than the ambient pressure, then the nozzle is choked. If it is less than the ambient pressure, then the nozzle is unchoked. And based on that, you will choose a different temperature and velocity ratio formula. And finally, you will find V9. Once you find V9, you have performance parameters that you need to find out, which is thrust, TSFC, propulsive efficiency, thermal efficiency, and the overall efficiency. Now the thrust is coming from both fan and the core engine. Till now we just used m dot core 1 plus f v9 minus b infinity plus a9 into p9 minus b infinity. Now in addition, what we also have is the fan thrust, which is m dot fan into v10 minus v infinity. The 10 terminal is for the fan, okay, and a10 into p10 minus p infinity. So this is fan side, this is core side. So you have two thrusts, and TSFC is going to be, since in the fan you're not adding any fuel, so this TSFC is going to be much lower. So that is why we typically use the turbofan engines for commercial purposes. And similarly, the propulsive efficiency, you do not just add the kinetic energy wasted from the core engine, you also additionally add a kinetic energy wasted from the bypass stream. Okay, so those are the updates. We will anyway solve one problem so that you will understand this. And I no need to explain this, how the effect of fan pressure ratio increases with the thrust and other things. So maybe I can explain this. The effect of fan pressure ratio is like, um, as you increase the fan pressure ratio, you are increasing the pressure which is coming out of the fan, and hence it can be at higher pressure. Since the air coming to the fan nozzle is at higher pressure, the exit velocity will also be higher, because you can establish a strong pressure gradient across the nozzle, hence your velocity will be high. So you expect the thrust to continuously increase, that is what you see, and hence the specific thrust also to increase. And since the thrust increases, TSFC reduces, because this thrust increase that you are getting is, you are not getting it by adding a afterburner, right? In afterburner we add fuel in, and then uh, we get an increase in thrust. This thrust increase is not by adding fuel, it's just by increasing the fan pressure ratio. So F remains the same, so that's why you see a drop in TSFC. And similarly, the propulsive efficiency and thermal efficiency is going to rise, because you're not spending fuel for this increase in thrust. So that's what you see here. And certainly the propulsive efficiency does not drop, because the since you're not adding any fuel in the fan stream, your velocity at the exit is going to be more and more equal to the flight velocity, and it cannot exit the flight velocity. So that's why, um, as velocity increases, you are going to go and reach a propulsive efficiency of very high propulsive efficiency. Not It does not go above it, right? um yeah, so those are the things: thermal efficiency and compressor pressure ratio. These I think we already saw in the turbojet engines itself. Similar uh, curves. Bypass ratio, again, since if you increase the bypass ratio, your but see, here the bypass ratio, effect of bypass ratio, when there is a same m dot. So m dot which is entering the engine is same, but I'm just reducing the core and increasing the fan, or um, the diameter of air intake is same, which means I am reducing the core. By increasing the bypass ratio, I am just reducing the core. If I reduce the core, the amount of air going through the core reduces, so its uh, hot thrust or the core thrust is going to keep on reducing, but the cold thrust is going to be increasing because of the bypass stream. So, but if you add its effect, it is going to be something like this, right? It is a competing effect between hot thrust and cold thrust. So it depends on which one overtakes the other one. So in that way, it is going to decrease like this. Similarly, with the specific thrust is per unit m dot does not change, and since thrust is decreasing, st has to decrease. So that's why you see here. And tsfc again, of course, it will decrease because you reducing the core means reducing the fuel that you are adding. So fuel reduces, so C tsfc has to reduce, and the propulse efficiency is going to continue to rise because the overall exit velocity is going to keep on reducing because you are increasing the bypass. If you increase the bypass, we know the bypass exit velocity is lower, and it's more close to the flight speed, and hence propulse efficiency is higher. The same goes with the thermal efficiency, but it reaches a peak because after that, the amount of fuel that you need to add in the core engine to sustain the thrust will be very, very high. That's why you see a very small drop after that. So these are the effects of bypass ratio, turbine entry temperature. You guys must know, have studied this long. Ground and cruise conditions. I'm not going to get into details, but if you have any doubts in this, you please feel free to stop me and ask. Um, so this is what we studied in the last week. In the next week, we will be studying forward fan unmixed two spool configuration. Um, then we will also have like in two spool itself we have like two variants, um, and then we'll also have three spool configuration. So we will study that in subsequent weeks. All right. So that is a brief, uh, you know, uh, a brief way to revise what happened in the week 5. So this is the TS graph. So it's so additionally what we have is from 2 to 8 you have a compression additionally, and from 8 to 3 you have a compressor. So this 2 to 8 is the fan here, and otherwise everything is same. Finally you have core nozzle exit, and in addition what you have this additional 8 to 10 uh, you know nozzle exit, which is nothing but your fan nozzle. Okay, so these are the major updates in the TS diagram, and this is the classification. We just saw this. Um, so to give an idea of about how isentropic process is, this is for isentropic process during flight condition. Um, and if you are in a ground condition, you are going to start up with some higher pressure, and when it is at higher pressure, you're not changing the TT4. Okay, you are going to have a lower area. Okay, so this is so the curve bounded by 2, 8, 3, 4, 5, 6, 9, and 2 is the work done, is the total amount of power that is used in this cycle. Now, if it is running at the ground, its pressure is high, so you will end up having less power. And if you increase the pressure ratio, how this will change is if you keep the TT4 same, then you will end up having higher pressure ratio from P03 to P03 dash. But what is also true is since TT4 is same, your amount of fuel that you add is less. So that is how if you increase the pressure ratio, fuel addition will be lower, and hence the thermal efficiency will be higher. So the amount of fuel will be less, and you will be able to expand it in this way. But one thing you should notice, the area under this curve, the black line and the red line is keep on changing. Okay, so um, up to a certain extent this area under the curve would be positive. So if you keep increasing from P03 to P03 dash, to a certain extent this will be keep on it will be the area would be higher than this black curve, but after a certain time this becomes smaller and smaller. So that's why you see a uh, peak in the thrust curve. So you will not get enough thrust out. Okay, so there is an optimal pressure ratio is what I trying to establish here. This is what we studied in the last week also, last week lectures. There is an optimal pressure ratio for which you will get a optimal efficiency. Okay. All right. Um, I hope there are no questions. If there are any questions, please feel free to stop me in between. Also, whoever is going to view this in YouTube, if you have any questions, please uh, use this platform. Maybe you can join next week to, if you have any doubts, you can clarify them. Okay. So this is the question I have for today's class. It is about a turbofan engine. Here we have to calculate the specific thrust and fuel to air ratio for the following case. One simplifying assumptions that we are making here is we are going to assume that all the processes are isentropic, which means there is no efficiency coming into the picture in this case. Okay. Um, so the flight Mach number is zero point 0.8 and it is flying at an altitude of 34,000 feet, where the ambient pressure and temperature are given. The fan pressure ratio is 1.5, the compressor pressure ratio is 6.5, and the bypass ratio is 1.2. So you should note that the fan pressure ratio and bypass ratio is an additional input that has been given here because it's a turbofan engine. Uh, the fuel heating value of the fuel is 45,000 kilojoules per kg. A specific heat of gases, air and gases are given. Maximum cycle temperature is 1600 Kelvin. Okay. Um, so this is the given conditions. We are going to assume there are no losses, Cp and gamma. Gamma we are going to assume it is 1.4 for both air and the gases that are exiting the combustion chamber. And what we need to find out is specific thrust and fuel to air ratio. So you should note that here the mass flow rate of air is not given. So that's why they are not asking for thrust. So thrust requires mass flow rate of the air. Here they are asking just for specific thrust. Okay, which means thrust per unit mass flow rate of the air. All right. So it's the same procedure. We are not. There is no change. Only additional components you need to calculate. So as usual, we will start from inlet. From inlet, we will find out what is P02 and T02, and once the once the air passes the inlet, it goes through the fan. Okay, so the entire m dot infinity, whatever enters the engine, will go through the fan, and the fan has a pressure ratio of 1.5, and after the fan is where the core and bypass divides. Okay, so after the fan, some amount of the mass flow rate enters the compressor. So the fan exit is P08 and T08, and the compressor pressure ratio is 6.5, and exit of the compressor is P03 and T03, and it goes through the combustor. We add fuel, we know what is the turbine entry temperature T04. Based on that, we will find fuel flow rate, and also if we have pressure losses, we will include that. Since this is an isentropic process with no losses, we will have same pressure. P03 and P04 will be same. And now we have turbine. Turbine requires you to find work done by in the compressor and the fan. And if you do that energy balance, you will get P05 and T05. And it goes through the tailpipe, no losses again, P06 and T06. And then it goes through the nozzle. This is a core nozzle. Okay, core engine nozzle, where you get P9, T9 and V9. Once you get this P9, T9 and V9, you can find the performance parameter. But this is still in the core. The remaining portion of the air which leaves the fan is going to go through the bypass stream, where you just have another nozzle. Okay, so this is just a fan nozzle where you have uh, where it gets expanded in the nozzle and exits as P10, T10 and V10. Using this, you will also include this as an additional thrust in your performance parameters. Uh, you add this as an additional thrust and you find the thrust and specific thrust and DSFC and all the other things. Okay. So as I said, you have fan, nozzle, and some changes in the energy balance of turbine is what you need to do. All right. So the first component is inlet. The inlet, we know that the air enters at M infinity of zero point 0.8, Mach of 0.8, and P infinity is 24.72 kilopascal and T infinity is 210 Kelvin. Since it's an isentropic process, you can just directly find T naught 2, which is going to be 248.16 Kelvin. Okay, and similarly, you also have P naught 2, which is also it does not have a diffuser efficiency. So if you just substitute these values, which is 24.72 kilopascal, and enters at point 0.8, so you will end up having the stagnation pressure to be 37.652 kilopascal. So these are the stagnation pressure and temperature at the inlet of the engine, and that is same even at the exit of the engine because inlet is an isentropic process. Um Now this enters the fan. In fan, you are increasing the pressure by giving the work. Your pressure at the exit of the fan is going to be 1.5 times the 37.682 kilopascal, which is nothing but 56.522 kilopascal. Now, the T08 is going to be based on the fan pressure ratio. You can easily find out to be 1.128 times the T02. Uh, so the stagnation temperature across the fan increases because you are adding the work, right? In the fan, you are adding the work, so stagnation pressure has to increase, and also stagnation temperature. So the temperature increases to 278.64 Kelvin. Okay, so now the two streams are divided. Now one of the stream is going into the core region where it goes through compressor and all other components. So first we are going to solve that side of the engine. So in the core flow, your P08 and T08 is 56.52 kilopascal and 278.64 Kelvin, and the compressor pressure ratio is 6.5. So from 56.52, it rises to 6.5. It rises 6.5 times the pressure. So that will be around 367.38 kilopascal. Okay. Now, um, the temperature again you can find out from the pressure ratio, since you do not have efficiency here. It simplifies the problem very easily. So the temperature ratio is 1.707, and if you calculate the temperature at the exit of the compressor, it's going to be 475.67 Kelvin. Okay. Um, so if you have a calculator with you, please cross check these numbers. Uh, I have calculated it correctly, but there might be some arithmetic mistakes. So please cross check these numbers. All right. So after compressor, you have combustor. In combustor, as usual, we'll do energy balance from T03 of 475.67 Kelvin. The temperature of the gases has to increase to 1600 Kelvin. And we are going to do it by introducing fuel and combusting that fuel inside the combustor. So since there are no pressure losses, P03 and P04 is going to remain same. Energy balance is nothing but m dot core. Okay, so there is one more change here. M dot core, not m dot infinity. M dot core times CPC times T03. CPT is the enthalpy with which the air enters the combustor, plus m dot f into QH is equal to m dot core plus m dot f into CPH T04. Okay. Um, so the f is now defined as m dot f by m dot core, not m dot f by m dot infinity. Okay, m dot infinity has both m dot core and m dot bypass. Okay, please remember that. So now the fuel air to fuel ratio is defined as m dot fuel by m dot core, not m dot infinity. Here we have T04, T03, everything else we know. So you just substitute these numbers, you will end up having the fuel to air ratio to be 0.03148. Okay. Now we found the fuel to air ratio. We know T04 and we know P04. We can proceed with the calculations of turbine. For the turbine, you need to do again an energy balance, and this energy balance should also include the uh, work done on the air in the fan. Okay, so the energy balance here you have is in the turbine you have m dot core flowing, not m dot bypass. So you have m dot core times 1 plus f is the total mass flow rate that is taken by the turbine, times CPH into T04 minus T05 is the total temperature change, right? Stagnation temperature change. So this is the total work done work extracted by the turbine, which is equal to the work done on the compressor and work done on the fan. Okay, so in work done on the compressor, again the compressor is operating for the m dot core. So you have m dot core CPC into T03 minus T08. So this part 303 minus T08. Okay. Now, uh, in addition, the same some more work is provided to fan, because fan does not rotate by itself. So you need to give some work to the fan, and that is from m dot core plus m dot fan. So fan is operating between the entire m dot infinity. Okay, so that's why you write it as m dot core plus m dot fan CPC times T08 minus T02. Okay, so that's the temperature change across the fan. So this is the energy balance. This is the change in the energy balance you have to do. Work extracted by the turbine is equal to work done in the compressor plus work provided to the compressor plus work provided to the fan. Okay. Now, if uh, uh, you know divide the entire equation by m dot core, you will end up and also rearrange it in this way, then you will end up having this as your relation. You no need to remember this, you just use this energy balance. Okay, you divide it by m dot core, and then here what you need is, so if you divide it by m dot core, you will end up having, here you will not have m dot core, here also you do not have m dot core, here you will have 1 plus m dot fan by m dot core, and m dot fan by m dot core is nothing but your beta bypass ratio, which was given as 1.2 in the problem, right? So you have 1 plus beta here, you have 1 plus f here, yf we just found, cph cpc we know, t04 we know, t03 we know, t08, t02, everything else we know. We only need to find t05. So you just rearrange it in this way, and finally you substitute all the values and you will end up having t05. So from 1600 Kelvin, your T05 reduces to 12,860 86.3 Kelvin. Okay, so that is your temperature at the exit of the turbine, and similarly you can also find the pressure ratio. Pressure ratio can be simply expressed as the turbine temperature ratio, and if you do this calculation, you will end up having a pressure of 214.54 kilopascal. So across turbine, the pressure reduces from 367.38 to 214.54 kilopascal. Tailpipe, as usual, there is no losses. So P05 and P06 are same, T05 and T06 are same. And this hot gases goes through the nozzle, gets expanded to the pressures. For that, we need to find out use the critical condition to find out at what pressure it exits the engine. So the choking condition is something like this. You do not have nozzle efficiency. That's why the complicated 1 by 1 plus 1 by eta n, that formula is not here. So this gives you the critical pressure as 113.34 kilopascal, which is certainly higher than the P infinity. At 34,000 feet, your ambient pressure is 24.72 kilopascal. So this 113.34 kilopascal is higher than the 24.72 kilopascal. Then the nozzle is choked, and hence it's choked. Your exit pressure is 113.34 kilopascal. You can also find the temperature, which is now, since the nozzle is choked, Mach number at the exit of the nozzle is 1. So T by T naught by T is nothing but 1 plus gamma minus 1 by 2 times m. If you rearrange, gamma plus 1 by 2 we will get. Okay. This corresponds to around T9 is to be around 1079.92 Kelvin, and hence your V9 is around 701.6 meters per second. So the gases exits the nozzle with a temperature of 1070 Kelvin and with a velocity of 701 meters per second. Okay, so this is core flow. Now, one remaining thing is in the bypass flow, the air which got compressed in the fan is P08, and it enters the nozzle at P08 and T08, which is 56522 kilopascal and 278.64 Kelvin. Now this expands in the fan nozzle. So let's try to find out the critical pressure ratio. So critical pressure is around 29.86 kilopascal. which is again slightly higher than 24.72 kilopascal. Since it's higher, again the nozzle is choked, and hence your exit pressure is same as the critical pressure, which is 29.89 kilopascal. And the temperature is going to be, again you can rearrange it, you will end up having 232.2 Kelvin. Okay. Now the velocity here is going to be very less because your temperature is only 232.2 Kelvin. So although the Mach number at the exit of both core nozzle and the fan nozzle is 1, the velocity at the exit of core nozzle is 700 meters per second, but velocity at the exit of fan nozzle is 305 meters per second. This the reason is in the core you have a very hot gases, and hence your speed of sound is high. In fan nozzle you have a colder gases, your speed of sound is low, and hence your velocity is also low, 305.5 meters per second. Okay. Now finally you need to find out thrust. Again you cannot find thrust because m dot core is not given. Instead uh, m dot core or m dot fan or nothing is given. We were asked to find the specific thrust, so it has to be a thrust per unit m dot core. So I just took the thrust. So the thrust relation has m dot core into 1 plus f v9 minus v infinity plus the pressure thrust at the exit of the core plus m dot fan into v10 minus v infinity plus A10 into the exit of fan nozzle. Also you have a pressure thrust. So that is the, so these are the four terms you should have in the thrust, and you divide it by m dot core, you will end up having this relation. Since here we need to know m dot core to find out the pressure thrust. At this stage you cannot find out because we do not have m dot core given in the problem, so we are just going to neglect the pressure thrust, the second and the fourth term. Okay. So the v infinity is around 273.9 meters per second. So from m infinity you can find the v infinity, and ignoring the pressure contribution, your specific thrust is going to be simply m1 plus f v9 minus v infinity plus beta times v10 minus v infinity. Okay. So now if you substitute it, you have this 1.2 bypass ratio here, and you have core nozzle, you have the uh, contributions from the fan nozzle, and you will end up having the specific thrust of 566.93 newtons per kilogram or kilogram second of the core air. Okay, so please be careful with the units. Although this is like you might say newton per kilogram of kilogram per second, but kilogram per second of core air or the entire air, you should be very careful. Okay, here it is in terms of core air we are defining the specific thrust. Okay. All right. So that is one thing. There is also, what else we need to find out? We need to also find out fuel to air ratio. So that we already found out. The fuel to air ratio is nothing but where is it? 0.03148. So again, here if you want to think about what is the unit, although fuel to air ratio, it's a ratio, it does not have a unit. Um, but here it is about kilogram of fuel per unit kilogram of core air, or to be specific, kilogram per second of fuel divided by kilogram per second of core air. Okay, not the entire air, intake air. Okay, so that is the change in the definitions. So maybe in your assignment questions, if they ask to express the specific thrust in terms of the kilogram per second of air, then you cannot let's say use this number. You have to divide it by the entire mass flow rate. Okay, if it is expressed in terms of kilogram per second of core air, if they asked you to write in terms of kilogram per second of core air, you have to express it appropriately. So that's why you need to know what is the unit in this, especially in turbofan engines. In turbojet engines we didn't care, here we need to be very careful. Okay. So so that is the uh, So that is the question we have here. So here I deliberately chose that, let's say if we not give m dot, we should be still be able to find out the specific thrust and fuel to air ratio. All right. So if you have any questions, please let me know. I will be in this call for another an hour or so. So next week we will, talk about turbofan engines with two spool configuration. So here it's just a single spool. In two spools, what you have is you have compressor and fan. Now you can either uh, now the compressor will also have be held in. Now the compressor will also be divided into low pressure compressor and high pressure compressor, and turbine also will be divided into high pressure turbine and low pressure turbine. Now the thing is, a high pressure turbine will, run either it can run only high pressure compressor, and low pressure turbine can run low pressure compressor and the fan, or the other way, other configuration is high pressure turbine will run both low pressure uh, compressor and the high pressure compressor, and the low pressure turbine will just run the fan. Okay, so there are two different configurations. You can do this in the turbofan engine. So we will solve one of that configuration in the next week. Okay. All right. So if you have any doubts, please stay back and ask. If not, I will meet you guys in the next week. Okay. Thank you. Thanks for joining.
Sir, hello.
Yes. Yes. Please go ahead.
Sir, in nozzle, while calculating that exit velocity,
Mm-hmm.
for unchoked nozzle only, we are considering the efficiency, nozzle efficiency. For choked nozzle, we are not considering the efficiency. Is there any
Mm-mm.
reason?
No, it's actually not like that. We will have to consider efficiency both in unchoked and choked nozzle. So the unchoked and choked nozzle differs only with the critical pressure ratio. So if you look at this expression, this is for unchoked. Okay. So if you
Okay.
the critical pressure ratio you have here does not depend on. So if you have nozzle efficiency, you have to use this relation with the nozzle efficiency and then find the critical pressure ratio. And that critical pressure ratio should be greater than the ambient pressure if it is choked. If it is less, then it is unchoked. And if it is unchoked, you have to use these relations. And you can see that for V9, so the pressure, if it is unchoked, the pressure at the exit is same as ambient, so there is no calculation in that. Okay, and temperature is actually simply you can express in function of pressure ratio, so that is no big deal. Only thing is while calculating the exit velocity, now you have a nozzle efficiency here. Okay, this is the isentropic efficiency of nozzle, which is also included while calculating the efficiency of the while calculating the velocity of the air at the exit of the nozzle. Okay, so anyway you will have to include, if the efficiency is given, you will have to include whether the nozzle is choked or not, doesn't matter, you have to include the efficiency. Is that clear?
Uh, yeah, but in chalk nozzle, while calculating that exit velocity, we are just considering root gamma RT
Mm-hmm.
and
Right, right. Okay, so I understood. In choke nozzle, we know a nozzle is choked and Mach number is 1. So velocity at the exit is going to be same as the speed of sound. So in that cases, it doesn't matter what is your efficiency. It is going to be equal to the speed of sound. And this definition of speed of sound is not going to vary because of the efficiency of the nozzle, right? Speed of sound is a inherent property of the gas. It is not going to vary whether it is in the nozzle or it is in the compressor, it doesn't matter. If you say at the exit, if you say the nozzle is choked and Mach number is 1, Mach number 1 is defined already by the speed of sound. So V9 is directly equal to the speed of sound. So here we do not use the efficiency uh, here. Okay. So it doesn't
okay,
it
thank you.
doesn't mean that efficiency is not there. Okay, efficiency is there. If you, in fact, if you look at it, the critical pressure ratio, the critical pressure that you found depends on efficiency, right?
Yeah.
Yeah. So critical pressure already depends on efficiency, and velocity. since it's equal to the speed of sound, it doesn't really matter. You no need to include efficiency into it, okay? Because it's an
Oh,
inherent
oh,
property of the gas.
okay, thank you, sir. So,
All right.
one more thing.
Mm-hmm.
After the air is passing through the fan,
Mm-hmm.
it will split into like some portion will go to core and some portion will go to fan.
Correct.
Like it will bypass. So
Correct.
the velocity, the pressure gradient across the fan will be different, right? Like
Correct.
what it is like what the compressor receiving will be some different pressure comparing to the our bypass.
Uh, Actually, if you look at it, so after the fan, um, some amount of air goes into the core, some amount of air goes into the bypass. So after the
Okay.
fan only it is splitting, right? So whatever the fan does is for the entire air. Okay, I understand. So this is like core is very near. Whatever air that enters, nearby the core will enter the core engine. Whatever the air that is going outside in the outer portion of the fan will enter
Yeah.
the. I understand those. That is like very minor pressure differences. So that you no need to worry. So this is about across the fan, the pressure is going to rise, and after that, that air stream is divided into two. So it is divided at the
Okay.
same pressure. Okay, whatever compressor sees is same as whatever exited by the fan. Okay,
Okay. So
does
like
that clear you?
along the blade length, the velocity will the angular velocity will change, right?
Along the blade, it
So
is true. Yeah.
that effect will not come into this.
Right. So that will be very minor. So across the fan, your pressure is going to rise. Okay. So, and
Okay.
also we are dealing in terms of not static pressures and static temperatures. We are dealing in terms of stagnation pressure and stagnation temperature. Right. So we are
Okay.
not really worried about what is exactly the velocity coming out of the nozzle or what is the pressure of the air coming out of the nozzle. Those things we are not worried. We are just worried about the stagnation pressure and stagnation temperature, if you look at it.
Okay.
So the
Okay.
stagnation pressure which is entering the core and also the bypass is same. But
Okay.
static pressure could be different because across the plate, different velocities it will enter. So static pressures will be different. So that
Okay.
doesn't matter for us for this
Okay.
calculation. Actually.
Okay. Understood.
Okay.
Okay. Thank you, sir.
All right, no problem.